Good morning, everyone. We're going to talk about building a feature store today. I'll talk about our decision to switch to Iceberg, but really I'm going to spend a lot of time talking about our architecture here at Featureform. Just realized my video's off. So yeah, first I want to just talk a bit about the problem statement, like what we aim to solve, and then I'll go into the solution and how we architected Featureform to properly solve it. So Featureform is a feature store. What we enable is for data scientists to deploy, manage, and monitor their features and productions. So really the data pipelines for machine learning is the parts that Featureform does. There's a few problems there. One is that when data scientists work, data scientists tend to work in a very kind of lightweight experimentation heavy mode using things like DuckDB, polars, pandas, etc., typically in notebooks. But in production, they have to kind of move these things over to prod, which includes a lot of uh, building streaming pipelines, building incremental processing on demand features. There's just so much other stuff that comes into play in prod, especially when you think about streaming processing. So there's this chasm between uh, experimentation and production. And part of Featureform's goal is to be the bridge, make it easier to get your features and your your feature pipelines out of your notebook and into production. So you don't get stuck with these situations where you have it working locally with a subset of data using pandas, but you're kind of unable to get that to production. We see two ways that people get their features into production today. One is that data scientists deploy their own. We think that this is actually correct, that data scientists should be able to deploy and manage their own feature pipelines. However, with the current set of tools and the current platforms that most companies have, it is not really feasible for data scientists to deploy production grade data pipelines. Because the data scientist already has, a lot of their expertise is very much in the model building side. And when you start worrying about things like managing incremental pipelines, tuning iceberg tables, all the things that kind of come into actual production data engineering, it tends to be out of scope. The other thing that we see probably more often is that data scientists and ML teams pass their features to the data eng side, to the data eng team. The problem there is that there's kind of a bottleneck. The data scientists are reliant on data engineers to actually get their features in production. And similarly, the data engineers are kind of getting bombarded with requests from the ML teams. So this is one thing that we set out to solve. How can we make it possible for data scientists to deploy production grade data pipelines for their features? Two is collaboration and organization. Because data scientist has that kind of very lightweight iterative workflow, a lot of the time they're moving very quickly, they're working in a lot of notebooks. And when they move things to production, sometimes it cannot be clear how those notebooks came together into the production pipeline or what the feature pipeline is at all. For example, we have a lot of situations where we see features in production, but the stuff that was built and created to get there includes untitled notebooks, variables called df final, tables like feature table v7, a lot of shell scripts that get run to actually get these things in production. It's super ad hoc and very painful. Once the feature's in production, the journey doesn't end there. Because features change, the data can drift, different things happen. There's a lot of stories of features moving or doing unexpected things and causing models to misbehave. And if you don't have monitoring on the feature serving, like the feature values that get served, you can end up in some really strange situations and not even catch it until the model pretty much breaks. And finally, there's governance and compliance, which I won't really talk about too much in this talk. So we have this problem. Data scientists need to get their features into production. We need to keep them organized, keep them versioned, and they need to have a level of reliability around them. Those are the things that we need. So we built Featureform to solve that. As I was thinking about in my last company, I had a data science team, and we were kind of considering how do we solve this problem for ourselves. And what I noticed or what I felt is that it kind of reminded me in a certain way of the problem we used to have of infrastructure before Terraform, where people would just like click open EC2 instances, run stuff, and it was impossible to keep track of what was actually deployed in production and what was being used and where it was being used. So we took that approach. Okay, the Terraform approach, how do we apply that to features? How do we build a Terraform for features? And that was the genesis of Featureform. So even the name Featureform is kind of a nod to Terraform. The way Terraform works, and just to kind of set the stage of how we built Featureform, is you define your infrastructure declaratively. You apply it. When you apply it, what you do is you change the state. So you kind of, there's this desired state. And all the rules of what is possible, what state can be changed, etc., that all happens in kind of the state level metadata. Once the state changes, there's another component that takes the current state in AWS, wherever, takes the state that you desire, the Terraform state, and makes changes to try to achieve the Terraform state. So you create a desired state, and then the thing runs and pretty much gets you into that desired state. So this is kind of Featureform's architecture. So I'm just going to talk quickly about this and zoom into the part that's really relevant. So Featureform, you can interact with it with two ways. One is the Python client or the CLI. That's how most people use it. And then there's also a dashboard, which I'll show in a bit. That's how you interact with it. Everything goes for Ingress. And there's really three components I want to zoom in on the top left. Featureform metadata, Featureform coordinator, and Featureform server. The metadata, that's where that state happens. So when you apply changes, Featureform takes a delta, and I'll give an example of this in a moment. It sees what's changed. It changes the state in metadata. There's this thing called the coordinator next door, which is pulling metadata for changes. As metadata changes, the coordinator's job is to take those changes and apply them to Snowflake and Dynamo or whatever you use. It could be Spark, it could be ClickHouse, it doesn't really matter. But it makes those changes in your production infrastructure so that those features that you built exist. And if it's unable to, then obviously it will monitor that, will give you errors, and you'll be able to see. Once that's done, you should have online features and your training sets available to you. And the Featureform server, its job is to actually pull that stuff and get it to you. So to recap so far, Featureform is a declarative way to define your features and your training sets. It allows you to declaratively define them, and then Featureform goes and actually interacts and coordinates your infrastructure to build those features for you. The core concepts, the core abstractions we have are providers. We have offline providers and inference providers. Offline providers are transforming, they're things like Spark or Snowflake. Inference is just for low latency lookups like Redis and Dynamo. We have data sets, both primary data sets, which is the raw data that you work with. Those could be, gold level tables and Databricks. They could be raw streams in Kafka. You define transformations on them, which create new data sets. And out of those transformations, you can define your features, your labels, and your training sets. So I'll give an example of this in a moment. Well, why don't I do that now? I'm going to walk you through a very simple example. So I'm going to switch to Um, uh, yeah, so here I have this. Oops, I'm gonna kill this because I don't really want to run these right now. Run that again. So here I have a CSV. I've defined it. I also have this thing in Snowflake. It's just a table. These are the primary data sets like we talked about. So the primary data sets, in this case, it's a table called transactions. I can retrieve as a data frame. It looks like this. This is the primary data that I work with in Featureform. In then I can define transformations. So here I have a Snowflake transformation. It runs in Snowflake. This is the definition. It's like Jinja. When I apply it, again, Featureform gets the metadata. It's like, okay, I have this new data set called transactions. Here's how it's defined. Here's the input. Here's the transformation. That shows up in the dashboard. So in the dashboard here, I can see my data sets. I can see that one specifically, or this is the original data set. I can see transformations, like that transaction transformation I'm going to create. So I can see all this stuff here. And you can see the task runs. The task runs, so once the metadata is stored, the task runs are kicked off, and then this actually runs and builds these data sets and eventually builds your features and training sets from it. So conceptually, what you're doing is you have a Python file or notebook. You define all your transformations. You can get more complex. You can even retrieve them, like here, as data frames. They're retrieved super quickly. We use Aeroflight. And then you can define your features and labels. I think I ran this wrong, but it doesn't really matter. You can see your features and labels and your training sets. So when you define these things, it allows you to, or what Featureform will do, like in this case, I have a feature, I specify it in Dynamo. Featureform will actually copy this to Dynamo for me. But I'm just declaratively defining this stuff so that all of it exists. And eventually, like here, I can retrieve my training sets as data frames and retrieve my features for any user. So that's how it works together. So coming back here, let's talk a bit about the typical workflow we see. So the typical workflow, going back to the first problem, one thing that's really important in Featureform is everything can be retrieved as a data frame. So you can work really quickly in a notebook environment. You could just create transformations, run things, retrieve things as data frames, run DuckDB on it, etc., iterate very quickly. Then what we typically see people do is they will have a directory in their GitHub repo called like Featureform. They'll write Python definitions, like Python files in there. They'll make a PR, they'll make the changes they want to make. That will be merged in, and then that whole directory gets applied. Featureform is smart enough to see the delta of what you do. So for example, let me show an example of that. If I reapply this, so if I do client.apply here, it happens instantaneously because it says it looks like an equivalent variant exists. So Featureform is smart enough to tell that, hey, nothing's changed here. I don't have to do anything. But if I change it, like I make this 200, and I apply it again, now it runs. Now, and also it creates a new version of it. It's immutable, so we'll create a new version. So you can see how this kind of works together. You would put all this in a Python file, you'd make your changes, you'd make your PR. If this value was going to get changed, then Featureform would just change the relevant data sets and nothing else. So going back to that Terraform analogy, when you apply, you change the state, and then Featureform will get the minimum delta of the state, the minimum change of features to build your features and training sets and actually go and apply them on your infrastructure. Great. And like I said at the beginning, if you have any questions, feel free to throw them in the Q&A. And if you're following along on LinkedIn, you can also put your questions there as well. Cool. So let's talk a bit about performance. So when we originally built Featureform, we built different implementations for like Snowflake, Spark, etc. So when you'd apply these things, you'd create these definitions, the coordinator, the part that would take the metadata and then make the changes and run jobs in Spark. Each of these things were separate implementations. We'd implement every provider completely differently. The problem there, one is that we had specialized implementations. So even for Spark, we had to have a different implementation for Kubernetes Spark, EMR Spark, and Databricks Spark. Because there's so many permutations of infrastructure, we weren't able to automatically optimize super well. So there was still some data engineer work to implement specific optimizations. And then on top of that, things could be kind of slow. We had, especially streaming pipelines and incremental pipelines, the way we handle schema changes, all that stuff was a bit ad hoc, and that made things very slow. We rewrote the whole Featureform implementation into Iceberg. So now how it works is all of these transformation providers actually create Iceberg tables. So all these tables are Iceberg. Iceberg tables allow you to create what essentially is like an index in a SQL database. So we can create indices and create our index pattern, how we partition, all the logic. We can really deeply specify how to store the tables for optimal transformations and optimal feature serving and training set creation once for Iceberg as a whole. And each of the transformation providers, all we need from them is to run the transformation right back to Iceberg. We specified Iceberg parameters. So it allowed us to unify everything under Iceberg. What that enabled, one, Iceberg automatically has snapshots and incremental changes. So every time you make a change in Iceberg, or you rerun an update, etc., it will just create a delta, and you can roll back. You can see what the delta was. It really allowed us to fine tune and control the changes that were made, which was super important for things like materialization, because we could just do delta materializations of that. We had merge on read. Merge on read allows us to write a ton of small files quickly. And then when we go run a transformation or a feature update, we can go and merge those things together. So what that allows for is much faster performance. And then probably the most important bit is our ability to use Iceberg's pushdown predicates. So I talked a bit about the indices. A pushdown predicate means that I can do something such as say, I'm going to partition a table by username. So A through C is in this directory, D through F is in this directory, etc. Now, when I do a where clause, I can skip reading all of the data that I know it's not in. I just can read the data where I know it's in this partition. So Spark does this automatically. So automatically, we make a lot of queries faster. The most important one, and the one that most people don't realize, is actually with joins. So typically, we would do joins. The joins became like a big bottleneck in our old implementation. Because when Spark does a join, it reads all the Parquet files from both tables. It has to sort them, which is a very expensive operation. And then it joins together. The reason it sorts is because it needs to so Spark runs across multiple nodes. It wants to put data that is that will be joined together between both tables on the same node. So there's a whole step where it's doing that. It's shuffling data around to all the different nodes for both tables so that the data that will be joined together is all together on the same node. This is extremely expensive operation. But with Iceberg, we're able to create indices, which we can actually store the table pre-sorted, for example. In that situation, when we do the join, it's already sorted in place. When we do writes, we can write in a way to keep things sorted, or we can choose to write quickly. And then when we do the join, we'll just sort the incremental data. There's all these tricks that we can take advantage of in Iceberg. And Spark has, and Snowflake, and nowadays pretty much everything, BigQuery, etc., has quite strong support for Iceberg. So I want to go a little bit under the hood of how Iceberg works and how we're able to achieve this. So in Iceberg, you create tables. Those tables are defined in a catalog. A catalog, all the catalog has is just a pointer to the metadata file, which is the global metadata file of the table state. The metadata file kind of through a few layers points to pointers. It's like pointers to pointers to pointers. And then finally, at the bottom, there are the actual data files. These data files are the actual data of your table. When you write an incremental change, so we see here on the left, we have S0, and on the right, you have S0, S1. The first write we did created S0. It was this manifest list. It had all these files with all these data files. When we wrote S1, so when we wrote more data to the table, rather than changing the existing Parquet files, what it did was it created new files. That became Delta. It created a new metadata file and said that table state is S0, which was the original table state, plus this delta S1. Now, when we going back to the idea of snapshots, I can go back to any point in state by going to the metadata file that was current at that point in time. I can also see the delta between the last change and this change is just S1. I can just read the delta. For the push down predicates, I can make it so that users A through C are all in this manifest file. And so I can create these partitions and sorting, etc. I can add all this metadata. And Spark and all these providers are smart enough to read that metadata and optimize their their query planner based on the state of the table. So Iceberg was really game changing for us. Now, the thing about Iceberg, especially Iceberg with Spark and similar, it's really complicated. There's like 100 parameters to tune for Iceberg. I didn't even talk about things like compaction and other things that keep your Iceberg tables healthy over time. So we know and we found that Iceberg dramatically increases performance and is extremely powerful, especially in conjunction with most big data providers. But like we talked about at the beginning, knowing how to properly tune Iceberg, Spark, etc., is pretty out of scope for most data scientists. So it's typically handled by data engineers. What Featureform enables is for data scientists to just define their features as code and have Featureform take that code, maintain a catalog, a state of your feature pipelines, and then actually turn that state into Iceberg tables under the hood and optimize those for you so that you as a data scientist have production grade performant data pipelines without having to worry about all the details. So that's how we built Featureform. That's obviously a very high level view, but it's open source. So everything I've talked about, you can see yourself, and you could always reach out if you have specific questions about how we implemented something or any design decisions we made. But I hope that was valuable. If you have any questions, feel free to throw them in the Q&A if you're in Zoom. And if you're on LinkedIn, you can also throw them in the LinkedIn comments. So I'll give it a minute, see if anyone has any questions. While we do that, Marie, do you want to talk about what happens next?
Sure. Yeah. And I'm looking on LinkedIn too. So if you have any questions on there, if you're watching on there, feel free to pop it in. But otherwise, thank you guys so much for attending this webinar. After this, I'll send you guys an email follow-up. Some of you guys reached out to me asking for if we do recordings. Yes, we do. We do the recordings on YouTube. After this, I'll send you the recording. And I'll also send you links to our GitHub repo if you want to start testing out Featureform yourself. And our Slack community, if you have any questions about Featureform, or if you just want to connect with people in the MLOps world. Other than that, thank you guys so much for attending the